Welcome back from lunch. We've had food for our stomachs. Now maybe time for a little more food for our minds. My name is Howard Lewis Shipp. I'm going to be talking to you today about the Clojure programming language. Clojure is something that's interesting and to me pretty exciting. And I gave this talk the rather grandiose title, Towards the Essence of Programming, because essences are, to me, very interesting and very exciting. So we'll start with the definition of essence, the intrinsic nature or indispensable quality of something. I mean, we all program every day. I program every day, all day, and it's really good to stay focused on what that really is. It's not necessarily the kinds of things that we do in our day-to-day jobs, but maybe it should be. One thing to think about in terms of the programming we do is just how many layers have crept into our day-to-day jobs. We have the operating system, the language, but now there's libraries, frameworks on top of those libraries, applications built on top of those frameworks. And on top of that, you have the JVM, the browser, all these other things going on. It feels kind of like we're writing one little tiny drop of code in this great big Olympic swimming pool of code. And that's great when it works, but it's a little horrifying when something somewhere is broken, not in your code, and you can't figure out where it is. So wouldn't it be nice if we could build systems more concisely, if we could build systems that worked with less code to manage? And I think Clojure is one example of how we can get to that kind of place. At the core of this is the concept of ceremony versus essence. This is a term originated by Stu Halloway. And it really gets at the idea that in the code that you write, there's some core bit of essence, some one little tiny bit of code that you need to have executed. And then if you're using a language, specifically a language like Java, you end up with a lot of ceremony around it. You have to take that little bit of code, that statement, that expression, and wrap it as a method and give it types and talk about what exception it throws, and then put that method inside a class and talk about its interfaces and other things. All that extra stuff between the code that's running, the code that you need to run, it acts as a glue, but it kind of gets in the way. The central concept here is your language, is the language you're working in, are the tools that you need to use to support that language, the things that that language expresses cleanly and easily, are those working for you or against you? If you're using Java, is it holding you back? Is it obscuring the patterns that you should be able to see in your code? Is it preventing you from expressing the design that you want to express, forcing you to do it Java's way rather than your way? Let's do some simple examples here. So up at the top of the screen, I'm showing a couple of stock objects that have simple properties, a ticker, name, the last trade value, open and closed prices, number of shares. And you can imagine if I had these in memory, I might want to sort them. And that's pretty simple in the Java world. I think the font is big enough so you can kind of make it out. We can create a comparator object and use the built-in collections.sort to sort this list of stock objects based on one of the properties. Now, what's the essence there? The essence is the line where we're comparing the last trade values of two different stock values to each other so that the rest of the machinery can get the objects into the right order. Seems plain enough. The ceremony around this really starts showing up when we see how much code we have to write again when we want to sort by the open price of our stocks rather than the trade price of our stocks. So much of that is boilerplate. So much of that is repetitive. And the essence of it is just the comparison of the two properties. And this is a consequence of working in an object-oriented language, where the data is encapsulated in private fields, perhaps, encapsulated inside methods, and methods are the only way to access your data. Now, the syntax up here is Clojure, and we're going to go into that syntax in a little bit more detail. But should be very familiar in some ways if you have used Groovy for the JVM or JavaScript in the browser, that we have maps, values, keys and values organized together. And that's very common in Clojures, to use dumb data structures, the built-in dumb data structures of Clojure, and put smart functions around them. So here we can see that our stock is represented as keys that have that odd colon name syntax and values. And then in the code, we can see that we can print out our portfolio of stocks, and Clojure will print those out. And there's a built-in sort by function built into Clojure. We tell it first what to sort on, what key to sort these objects on, and then we provide the list, the portfolio, and it does the sorting for us. And we can give it different property names. They're actually keywords that are used as the keys in the map. Or at the bottom example, I define a function called value@open, which simply multiplies the open key by the shares key. And now I can sort using that function to do the comparison, as opposed to, in Java world, creating a comparator just for that job. So the point is, we've got the data. The data is just out in the open. And with Clojure, you write functions to work on this sort of standard structure for your data. And you get a lot of benefits from that. So I'm going to dive into a little bit more about the language so we can discuss it at a better level. The first thing that you notice about Clojure is all those parentheses. I mean, it's not very familiar when you've been working in Java and C, and there's curly braces and brackets and semicolons, and you just get used to that. You see all those parentheses, and eventually you don't see anything but. Okay, panic ensues. Especially when you hit the end there, where we're closing off a whole bunch of expressions, and there's a lot of parentheses in a row. It seems pretty odd. In fact, Java is the odd thing. It's got so much less history than Lisp. Java being around since '95, and Lisp has been around since, believe it or not, the early '60s. So this is XKCD talking about this a few years ago. Elegant weapons from a more civilized age. And in fact, all those parentheses are doing is they're breaking up the stream of characters into little blocks. And in fact, once you use Clojure, or for that matter, any Lisp, once you use Clojure for a very short period of time, you're not any more aware of all those parentheses than you would be in Java code getting hung up about all the curly braces. They just fade into the background, and what you see is the structure of your code. And the structure is often much more evident in Lisp because it's so bare bones than it would be in Java. And in fact, when you compare a piece of code that does the same job, this is one that is printing out a JSON object to a stream as part of a servlet. This code here in Java is equivalent to the code I wrote earlier in Clojure. You notice that it actually ends up having the same number of characters of punctuation. So you have the Clojure code with its parentheses and a couple of square brackets versus the Java code with its curly braces and parentheses. And stripping out some documentation in white space, the Java version is actually longer and has the same number of nesting elements into it. In fact, as you use Clojure in a more advanced way, you end up having fewer of those things because there's so much in Clojure you can reuse and express far more succinctly than in Java. So why is Clojure in the structure that it is? Why is it using all these parentheses? Why can't it look like C or C# or Java? Well, it comes down to some basic aspects, some of the essences that I was alluding to earlier. When you have the compiler take a method like our conversion to Fahrenheit up there, when it executes, it parses these things by characters and then organizes them into a thing called an AST tree, an abstract syntax tree. Stuff I learned about, in college way too long ago. And these abstract syntax trees have a structure. And you can kind of see how it's looked at the expression. It's seen that the star, the multiplication operator, has higher precedence than addition. So it's built a structure that represents that says that we're going to add the result of doing the divide, and the divide is based on the result of doing the multiply. And from this, the compiler can generate, in Java's case, bytecode. Now, if you're at the analysis stage of an AST tree, and you're writing a compiler, you often want to print it out, and the representation on the right is actually very common, and it looks just like Lisp. And that's not exactly a coincidence. Okay, that's one way of representing that tree structure. And in fact, that's what you're doing in Clojure because it's a Lisp language. Now, Java doesn't have a very good intermediate representation. Once you take your code and compile it, that's the top box, you end up with bytecode that can be viewed like it was assembly code, or you end up with just a whole bunch of bytes in a file on the disk. There's no back and forth representation from the Java code to the code that actually executes. But in Clojure, form is structure. That code that we write stays as a data structure that can be looked at and manipulated. So the implementation of a function that does that conversion from Celsius to Fahrenheit looks just like the AST tree. In other words, you're sort of like the pre-compiler for Clojure. That's one not so fun way to look at it. Or it could be that you're more directly programming than you would be in Java. We've removed some layers. We've removed some syntactic sugar. And now you're getting to look at the code as it really kind of executes. So in Clojure, you have the idea of a list. A list is in parentheses and consists of some number of values on the inside. In the middle call is the standard one. When you see parentheses, that's a function call. So unlike Java, where you have the method name and then a parenthesis and then the parameters, in Clojure, because Clojure is a functional language with the the emphasis on functions, the function name comes first, and then all the parameters. If you want a list to just be a list, to not be evaluated as a function call, you put a leading quote outside the parentheses. That's the top case. And of course, the same syntax gets used and reused. So when you're defining a new function, it looks kind of like a function call. Def-n means define function. We give it a name. We give it some documentation. We tell it what parameters are available, x and y. And then the remainder of that function call, the def-n call, is the code that's going to get executed. So you have this great consistency front to back in Clojure. One thing that we don't expect because we've been using Java, we get used to that whole compile run approach. Early languages, especially Lisp, have REPLs, read, eval, print loops. In other words, you can interactively work with Clojure and test things out. In fact, I keep a window open whenever I'm developing Clojure code because I have a lousy memory. And I can't remember, the order of parameters sometimes. And I can look at the documentation, but often it's just easier to type out a little sample in the Clojure window to see if I got it right. So again, everything you can do in Clojure, you can do directly from the REPL. You can define new functions. You can execute them. You can do anything you need to do. And in fact, Clojure doesn't have an interpreter. Clojure is always compiled, whether it's compiling source files stored on the disk or compiling input from the REPL. All of that goes through the evaluator and turns directly into Java classes. As opposed to the Java world, we have source code on the disk, and it always goes through a separate Java compiler external to the virtual machine before turning into bytecode that can be executed by the machine. So if it works in the REPL, it just plain works, and it works at full speed. So Clojure allows for all the standard kinds of literals that you would expect in a language. Strings, it has a nice syntax for character literals. Nil is the same as Java null. True and false. It has a couple of interesting things, too. It has ratio types. So when I say 22/7 there, Clojure recognizes that and keeps it as that ratio and won't, if you multiply ratios by other ratios, it's sort of a non-lossy expression. So that's very handy if you're doing certain types of mathematics. An important part of Clojure is keywords. And you see this in other languages such as Ruby. Keywords are kind of like a string that doesn't have to be quoted. It just has that leading colon sign. And they're frequently used as keys on maps, as we saw in that first example with the stock ticker. And they're also kind of like enums in that they are singletons. They're unique. So :foo is always the exact same Java object internally to Clojure wherever you go, which, again, makes them really good at being keys on maps. So to talk about a functional language is often to talk about the data structures you can use in that functional language, and then the functions you can apply to those data structures. The classic data structure in Clojure, because Clojure is a list processing language, is the list. And here we're seeing a list, but it might look like internally storing a few numbers. The blue squares are called con cells. They store a pointer to a value and a pointer to the next cell. And one of the neat things about this is that when you want to add a value to the front of a list, you keep the original list, it's immutable, and you just add a new con cell on the front of it, pointing to it. So it's pretty natural to see how you can use that and say, yeah, lists never change, we just add new stuff onto the front of them and keep the old list as it is. So again, there's functions where you pass in values in a list and it gives you a new list. But that immutability is something that's very important to Clojure. And it actually applies to all of the data structures. That in Clojure, whenever you add or remove a key from a map or a value from a set, you get back a new immutable set or map that reflects the change that you made. Okay. Vectors are kind of like a list, except they're also kind of like an array. They have fast access to values by an index number. And a lot of the things that you can do with a list, like ask a list for its first value or everything but its first value, functions like first and rest, those functions also apply to vectors and to anything that looks like a sequence of values. And then maps are the most useful of the different data types in Clojure. This is where you store all your data. If you're pulling data from a web service, if you're reading a database, if you're reading a flat file, if you have something in memory, you're almost always going to pull it apart and represent it as maps. And then you're free to make all kinds of manipulations on those maps as you go. So there's functions to create maps. There's functions to get a value from a map. And what's interesting is a keyword can be put in that first position in a function call. It acts like a function and gets the corresponding value out of the map, which is why in that earlier example when we're sorting, we can either pass in a function or a keyword, and it accounts for the same thing. We either provide an explicit function or sort of the implicit function that a keyword is. A keyword acts as a function to extract its value from a map. And there's also sets. So all these are familiar basic data structures. What makes them interesting is how they worked together within the context of the language. And that's what gets into functional programming. And of course, functional programming, you get that association with, being the grizzled, bearded, techier than thou type. But it actually is something that we're probably all doing day to day. We're just not aware of it because we don't see it in the language as clearly as we should. Rewinding the clock way, way back to my very, very first program in BASIC, in junior high school or something, x equals x plus 1. And my math professor, my math teacher in high school, immediately said, no, it doesn't. She didn't know much about programming. She knew about math. And certainly the statement x equals x plus 1 is just false. Because in the world of mathematics, there is no case where a value is equal to itself plus 1. And that shows up in functional programming languages too, the idea that everything is immutable, that once a variable has a value, that value can never change. You might have some other value, a variable somewhere else that might have the same value or something similar, but everything's immutable. And this really throws people when they first look at Clojure or a functional programming language. They're like, well, if everything's immutable, how do I get anything done? And of course, the answer to that is twofold. First of all, there's the stack. Values get pushed onto the stack, functions get called, results come back on the stack. So that's kind of the mutable space in a functional programming language is the stack. And in Clojure, there's actually a number of mutable data structures as well, but you have very careful control over those to make sure that they work well in the JVM in highly concurrent programs. So Clojure has these excellent concurrency mechanics that actually aren't even part of this talk. They could be a whole talk unto themselves. But at the core of it, immutability is a central feature of most functional programming languages. And it actually shows up in the definition of function. A function in a mathematical sense is the idea that some input values completely determine your output values, regardless of time or anything else in the world. They're complete unto themselves. And immutability helps that. It means that you can defer evaluation of an expression till you absolutely need it, because you know that it's not based on any mutable state that some thread could come along and modify. And Clojure does this extensively. It defers the evaluation of things till they're actually needed. Functional programming means things are predictable. You have these small functions, again, certain inputs in, predictable output out, much easier to test than trying to set up mutable state in your objects and try to test them that way. So that's one of the things that's very exciting is to start building up your confidence in your code, that you know that when you test it, that test really does apply to the real world, to the production mode of your application. And as I was saying, isolation from time. If 1 + 2 = 3 now, 1 + 2 is going to equal 3 in a week or a year, regardless of what else has happened in your system in the meantime. And that scales up to all the other things that happen in real applications, information coming in, going out, and so forth. So the functional stuff starts coming into play when you start manipulating these data structures. So here I have a list of names, maybe from a file system. I want to filter out the ones that start with a period, much like Unix does when you do an ls. So Clojure has a built-in function for that, filter. And you pass in a function that does the evaluation. So the first version of that little expression, I define the function in line. Because you're doing so much with functions in Clojure, it makes it very succinct to define them. So I don't need to define a class. I don't have to come up with a method. I don't have to come up with anything. I just have the function right there, right in line. And it simply says, ask the string, does it start with a period? And when that's true, we'll keep the name. Otherwise, we'll discard it. Now, because you do that so often in Clojure, there's an even more succinct way of doing that. The hash mark parentheses, which defines an implicit function right there. So the first 2 lines are the same. And at the bottom, you can see how once we have our names, we can filter them. Or even more succinctly, we can use remove, which is a variation of filter, that removes the elements that match. So our code gets smaller and smaller. And this is one of the things that you see with Clojure is you're like your first day working on it, it seems like everything is pretty involved. You have to write a lot of code to get a little bit done. And as you become more familiar with both the language and the available functions in its built-in library, things get tighter and tighter and tighter and become shorter and shorter and easier to read. For me, the functional programming is kind of misnamed because the functions are important, but as important are the closures. Closures being the ability to have a function that knows some other information that customizes it. For instance, back to our filter. Maybe we want to be able to filter these files based on an extension. So that's just a matter of taking the file name and splitting it periods and looking at the last value. That's easy enough. But if we're doing that a lot, wouldn't it be nice if something could write that function for us each time we needed it? And again, that's something you do in a functional programming language. You have a function that takes a parameter and returns a new function. So our require extension is a function, but it's also a factory for functions. And the Clojure aspect is we pass in the extension, the file name extension we're interested in as a parameter. And the function that gets returned is a closure. It knows what that extension value is. So 2 different calls to this require extension will return 2 different, in Java terms, 2 different objects that know 2 different values for that ext parameter. So now we can start plugging these things together. The functional nature means that it's very easy to compose bigger and bigger functions and just click them all together. In Java and other typical object-oriented imperative procedural languages, you do everything in terms of steps. I got to do all of step A, and And then once I finish that, I can start working on step B and then step C. Whereas, so here, in order for me to, excuse me, here, in order for me to add up the values of all of these stocks, I have to do that. I iterate on my way down through the list of stock objects, and I get its open value for each one and add it to the result. And then I can return that single value. But when in Clojure, you do things instead in terms of a flow of transformations. You start with a list, and you say, I want to manipulate it in this way, and then that way, and you just keep chaining those results together. So for instance, if I'm interested in the open values of everything in my portfolio, I'll use a function called map, where I say, iterate over the maps in my portfolio, and for each one, extract one key. So we're going to say, go get the open key from each map and form a new list from that. So now I end up with a list of just the values I'm interested in from the initial data. That's a very simple kind of transformation. One of the things about the map function is it's lazy. Laziness is a virtue in languages. What we mean by lazy is that it calculates each successive value in that output list as it's needed. So if I use Clojure interactively, and I tell it to print out the result of a function called iterate, that's an infinite list, and it's going to run that forever. And yet, as we can see at the bottom, I can say, create this infinite list of numbers, starting from 1 and going forever, and take the first 20 values of those. Now, in the Java world, when we try to create that list initially, it would never get past that step. It would run until it ran out of memory. But in the Clojure world, it's completely reasonable, because that iterate function is lazy. So when we ask it for the first value in the list, we get it. When we ask it for the second value in the list, it calculates it, holds on to it, returns it, and so forth. We can even do things where we take two infinite lists and use a map on them to create yet another infinite list, and that too is lazy. So we can then just take the first few values from that. So this laziness is really powerful. It's lazy is kind of a weird term because Clojure is actually having to do some really complicated things to do this. It's kind of like Gromit in The Wrong Trousers. He's on this runaway train, and he's putting the track down in front of the train as fast as it can go. So what the map function does is it takes some input values and applies a function to each value and produces outputs, and it does it just as everything is necessary. So we can define functions like this last trade value and map it on our portfolio, and we get back a new list with just the values we want. Or we can do things that are more interesting. We can say, okay, let's pull a couple of values out of our stocks and form a new value from them. So we're forming a new key called last trade value. And again, those values only get calculated as we're interested in them. Another powerful feature is reduce. Reduce is how you take a list of data and reduce it down to a single value. So again, a function's at the core of it. That's how functions work in Clojure. Is we say, okay, here's a function that takes two values, does something to them, and returns just a single value. And by applying that function to each value from the list and then plugging the result back into that function, you eventually get down to a single value. So here we're saying that our reduce, we're using the reduce function, and our reducer is simply plus, the function that adds two values. So we're getting the last trade value from our portfolio, and we're adding them all together and eventually getting down to a single value. And what's fun is that you can use the same kind of approach to do things that you would think would take a lot more code. So here we're starting with an input string, and we're using a function that takes it apart character by character and tracks how many times each character appears. So that once we do that reduce, it starts with an empty map, takes the first character, sees that there's no key for that in the map, provides a key for it with the value 0, Then it gets the next character and the next character and the next character. It keeps building up that map, finding values in it and incrementing them if they're there or setting them to 1 if they're not. And what we get at the end is a map that's keyed on character values and has the number of times each character appears. So again, doing this in very, very little code. Lastly, there's things called list comprehensions. And this is a way to build up a list very handily. So my first example, I show that we're defining a suit of cards, a limited deck of cards where we have suit, hearts, clubs, spades, and diamonds, and then values for them, which range from the numbers 1 up to 3. And from this, we get a lazy list that represents all those different combinations. So hearts 1, hearts 2, hearts 3, clubs 1, clubs 2, club 3. And this can be used elsewhere. The latter values in this list comprehension can depend on the earlier values. So here we're saying we're going to count from 0 to 3 for x, and then for each y we're going to count from 0 to that x. So we end up with 0, 0 is the first value, and then 1 for x and 0 for y, and then 1, 1, and then so forth. So in, again, small amount of code, we can build up a lot of information. So the point of all this is that the functions fit together very nicely. You're able to take basic functions and using some of the built-in functions of Clojure, map, reduce, and so forth, you can add them together to get a lot of sophisticated behaviors. And it turns out that reuse in the functional world is actually easier than it is in the object-oriented world. So Paul Graham is a big proponent of Lisp, and he has this quote that object-oriented programming came out of like simulations. The first object-oriented programming language was a simulation language called Simula, and somehow ended up being the default language that we use for doing enterprise software. And it's not quite clear how or why that happened. And Lisp has a longer, better track history of supporting really good levels of code reuse, partly because it's not tied down to how data is represented inside objects. So that's some interesting stuff. Very low level, but it's kind of cool how everything fits together in Clojure. What gets really exciting with Clojure is this concept of language ownership. Who owns the Java programming language? Okay, Oracle apparently just bought it. There's the Java community process, however that works, that says we're going to make a change to the language, and in 8 or 10 years you'll get to see it. You've got smart people like Brian Getz or Mark Reinhold who are defining these new features for the language and debating them strongly and getting them right, and then again they show up a few years later. The short answer, though, is not you. You don't own the language. You do not own the Java language. You get to use the Java language. And that's because you don't really have control over the compiler. Short of taking OpenJDK and forking the compiler yourself, which is written in all kinds of crazy C and C++ and assembly, and figuring out how to make all that happen, and then convincing everyone you know to use it so that you can use your modified Java syntax, and maybe convince IDE manufacturers like Eclipse and JetBrains to support your new language features, you're not going to change the basic syntax of Java. You have to wait for someone else to do it and wait a good long time. Who owns Clojure? Could be this guy. This is Rich Hickey. He's the inventor of the language. He has write access to the repository. I guess he owns it. But the interesting thing about Clojure is that how much of the language is in fact written in Clojure. So this lazy map function that I showed before, that's just Clojure code. The vast majority of things you do in Clojure are written in Clojure, which means that a lot of the stuff that it does, you can do in your own code. Now, a key part of A key part of writing any language is how does evaluation work? And in fact, when we start talking about concurrency and laziness and all these other factors, when does evaluation work? So here I got an example. I've got a person, and maybe I'm going to be, maybe that person's a pharaoh who needs to be buried inside a pyramid. So I say, is the person a pharaoh? Is the person dead? Have we finished building their pyramid? Then we can entomb them. Okay? And notice the difference between the first example and the second. In the first example, I used the Java double ampersand, okay, the logical and operator. And it's short circuit. If the person isn't a pharaoh, it never gets any further than that in evaluating that expression. If I create temporary variables for each step, we lose that short circuiting, and suddenly everybody's getting a pyramid, whether they're a pharaoh or a slave. Okay, so controlling evaluation is pretty important there. Maybe we could do the same thing in Clojure. We'll say if all of these values are true, and we'll say, is the person a pharaoh? Is the person dead? Have we finished building them a pyramid? Then we'll entomb the person. And I can define my own all true. Yes, there's a built-in thing in Clojure called and, but if I didn't want to use it, I could write my own, where I just say, are all the values true? Kind of like what a static method would look like. So if I wrote the equivalent thing in Java as a static method, it would just iterate over the Booleans, return false if any of them were false, and then return true. And that has the same problem. Because we're evaluating all of the parameters ahead of time, we will end up creating pyramids for people who aren't dead and aren't pharaohs. In Clojure code, you're going to use and. And short circuits. It only evaluates enough of the expression to get a result. So if the person isn't a pharaoh, that's going to be false, and it's going to short circuit. It's going to stop evaluating at that point. So and actually isn't a function. It's something else in Clojure. It's a macro. And when you hear macro, you start thinking, if you have a C background, oh no, C macros, which operate at like the character level, way before the compiler, and cause a lot of grief and if-defs. In fact, a lot of Java was a reaction to the use of macros in the C language. The Java language designs a different way to attain portability. But macros in Lisp and Clojure are quite a bit different from that. Of course, this is the head exploding zone. The most interesting parts of the language are the parts that will make you a little bit nervous. Clojure, as it parses input character by character, it turns it into what it calls forms. And those forms might be literal strings. We have the square brackets that represent vectors. We have quoted lists. We have maps inside curly braces. We have sets. And then we have all the other sort of list forms like function calls. If is a special form. A special form represents something that's built right into the language. Unlike map and a lot of the other stuff, it's actually part of the Java code of Clojure. And it short circuits. It says, okay, I'm going to run a test, and then I'll either evaluate the first expression, or if the test is false, I'll evaluate the second expression. Okay, so in functional programming, you have something that looks like a function to do ifs and thens. Macros fit into the overall scheme of things. In Clojure, you have the reader that reads character by character and turns things into forms. And then the evaluator includes this macro expansion phase. And then the output of that is what actually is used to create bytecode. Macro expansion can take something like that and statement, and it expands it out. It says, okay, the and goes away, and we sort of recursively expand it into a nested series of these ifs. So you can see that we really have encapsulated that concept that if the pharaoh is, if the person's a pharaoh, then we continue into the nested if to do the next check. Otherwise, we can short circuit. So we have that control over evaluation. And in fact, there's a special form in Clojure called def macro, just like there's one for defining functions. And we provide a kind of template that guides it in how to do the expansion. And expansion's recursive. One level of expansion below says, okay, we're going to take if and then and we're going to take that first term, the if pharaoh person, and we're going to move it up. We're going to evaluate it once. We're going to put in a temporary local variable. If it's true, then we'll continue on with the and macro to do the remainder of the evaluation. Otherwise, we'll return that false value. And then only if that's true do we entomb the person. So one macro expansion often results in new macros that themselves have to be recursively expanded. So what we've done here is we've expanded the language. We've provided the link between what comes in terms of forms from the reader. Using the macros, we eventually can reduce everything down to one of the few couple of special forms, and those are the ones that turn into actual bytecode that executes. And you can use this really effectively. You can use this to create domain-specific languages or just otherwise remove all kinds of boilerplate code. So here I have an example from some test I wrote for Cascade, which is a little web framework I was working on. I'm using a Java library called EasyMock to create mock objects. And there's a lot of ceremony there. There's a lot of boilerplate of me creating mock objects and setting them up and getting them ready and then using them in my test and checking that everything occurred correctly. And I was able to write a macro called with mocks that encapsulates all of that boilerplate work for me. And so I'm actually writing a new subset of Clojure just for doing this specific kind of mock testing. And it takes care of all the details for me, which is very nice. In the Java world, if I wanted to add some of these features, it'd be necessary to, write a JSR and get someone to work on it and wait a few years. Instead, I was able to write it in a few minutes and make use of it immediately. Another part of this Cascade language is a domain-specific language for building up a DOM structure. So instead of having templates as an XML file the way I do in Apache Tapestry, I wanted the templates to just be inline code mixed in with the other Clojure code. And so I have a special macro called template that does that. It looks for keywords and assumes that those are elements. And it looks for a vector next to the keyword and assumes that's the body of that element. And this turns into a function that builds that structure from the bottom to top. Because again, everything's immutable. So you build from the bottom upwards because once you create a structure, it's not as efficient to modify it. Since you don't really modify, you just create a mutated copy. Anyway, the point is that this structure is partly static. The title is always going to be Cascade blog. The class is always going to be recent postings. But other parts of it are Clojure code. And this all gets mixed together. In fact, the result of the template is a call to all kinds of internal functions inside the Cascade library that looks more like traditional code, but it's very verbose to do all the things it needs to do. And what I'd rather do, what I'd rather have is succinct code and let Clojure do all the heavy lifting behind the scenes. So getting back to this term, this essence, this intrinsic nature, indispensable quality, what is, the essence of programming? Here's one quote that kind of led me most of the way. Controlling complexity is the essence of programming. But I think he's a little too specific. I think control is the essence of programming. And by control, I mean control over how things are evaluated or when they're evaluated. And what we have is that Clojure is both a language and a language toolkit, both in the same bundle. And that's where the control comes from, that you can take this basic language and extend it to do exactly what you need. And you can do it quite clearly and easily. So it's a little bit to read here. But here's another XKCD where the unnamed protagonist, gets a vision of the world as structured in terms of Lisp, and then finds out it was all hacked together with Perl. Kind of disappointing. So there's tons more to discuss about Clojure. In fact, there's a whole conference just devoted to Clojure itself. It's coming up on a 1.3 release that's adding a lot of new features. Excuse me. And again, something I didn't get into in this talk is how fully it integrates with Java, which is really useful for leveraging all your existing code. There's a bunch of books out or coming for Clojure. And there's a lot of really good resources online to cover, excuse me, a lot of good resources online that go into a lot of detail that are good companions and good references to keep in addition to the books. My blog is tapestryjava.blogspot.com. I talk about Tapestry and Java and Clojure and other things. And finally, when I think about object-oriented programming, everyone likes to use the Legos metaphor. And it is true that, your objects can click together somewhat automatically in the Java world, though you often find all kinds of extra code or extra XML fitting them together. But it really feels like in the Clojure world, the functional world, you can build some really interesting things because everything fits together just so nicely. Okay, we have a couple of more minutes left for some Q&A.
Okay, I'll be the first one.
Thank you.
My question is, of course, what's your opinion? How would you compare Clojure with Scala? Because a lot of things I've seen is very similar to a language I can use already, and with much more books and conference. So, how would you convince me to use Clojure rather than Scala?
Okay. Normally I'd repeat the question, but it was very clear. This is like one of the first questions that come up, and in fact, I asked Rich Hickey the same question myself. How does Clojure and Scala compare? And his reaction was actually very diplomatic. He was like, well, they really apply to different things. How do they compare? I think Clojure is more definitively functional. Scala, by default, leans a little bit more towards mutable state, and it tries to align itself with object-oriented as an object-oriented functional hybrid. Scala has some great features. It also has a great deal of complexity. In fact, Neil Ford, who speaks a lot of these conferences, says that Scala fetishizes complexity in exactly the way that the Java community embraces. It is more complicated. It has the very complicated kind of brought in from Haskell approach to type. You have a very complicated type system that you have to understand to really leverage a lot of the features built into Scala. So that's not preventing people from getting stuff done, but it is a little bit of a barrier to entry. Now, on the flip side, Clojure has its barrier to entry, which is the syntax, which is so alien to people, whereas Scala has a more immediately understandable syntax. Thank you. What I really like about Clojure, and something I miss when I'm coding day to day, is the data types and the succinctness with which you can manipulate them, the immutability, and a lot of the concurrency features that I didn't have time to discuss today that work really pragmatically and effectively. And there's an aspect to Clojure, once you learn it a little bit, that all the bits and pieces, including the concurrency support and the immutable data types and the way functions work and the way namespaces work, everything works together. They're all pulling in the same direction. Where by comparison, other languages seem kind of clumsy after a fashion, where different bits and pieces work together, but they don't all follow the exact same design pattern. Certainly, there's been definitely a lot of explosive use of Scala, and we're also seeing some very explosive use of Clojure, and some very good organizations such as Relevance, a consulting company in the US, who have really embraced Clojure to the point of employing Rich Hickey to develop it.
Clojure looks amazing. I'm here, on your left.
Mm-hmm.
Okay, it looks amazing. Mm-hmm. However, you speak about functional programming. I'm not sure what it means exactly to integrate a functional programming language paradigm with an imperative language. Are there challenges regarding the resulting semantical models, the assumptions that you can make, things like that?
Okay. So the question is, you have Clojure, it's operating inside the JVM, and it's interoperating with Java objects. And how does that really work in practice? And there were a couple of hints of that in some of the slides where there's a very good syntax for invoking functions of Java objects, where you just put the dot and the method name first, and then the object is the first parameter. And it takes care of that. Clojure actually has very good interaction there. It's also possible to define Java classes entirely in Clojure. There's a syntax for that in Clojure 1.0 and 1.1 and 1.2, and an improved syntax and a more efficient runtime for that in 1.3, where you have Clojure code that gets turned into fully functioning Java objects that can be passed into the Java world, even to the point of extending from base classes, implementing interfaces, all of those types of things. One of the things that Rich and the team are working on, though, is really reducing the footprint of the hosting virtual machine to a bare minimum to make it easy to port Clojure into new platforms. So there's always been a .NET version of Clojure, but it's always lagged a bit behind the Java version. And I think they want to go further with that to make Clojure easier to interoperate with. But again, from Clojure code, you can invoke any method on a Java object. You can create objects. You can call methods, static methods, or instance methods. And it's also reasonable to take a Clojure object and pass it into Java code and have it be called back. In fact, Clojure Functions automatically implement a couple of interfaces, including runnable and comparable, I believe, automatically. So the interop story is actually really good. In practice, what you tend to see is that you try to isolate the Java code part of things as much as possible. So, I was doing some XML parsing in Clojure, and I was using, the standard Java SAX parser to do it. And, that's really a little bit ugly. It's designed as a Java API, and it's kind of built on the idea that you're going to do have a mutable object that you're going to fill in with values. I just isolated all that inside a namespace, inside a particular function. And so, the value you passed in was like a URL, and what you got back was a Clojure list, Clojure vector, representing what was parsed. And that's pretty standard, is take the Java code with all of its mutable state and questionable semantics and isolate it in such a way that the rest of your code can stay nice and pure.
What I like in Java is that the stack is quite wide, allowing me to build apps like web apps or even desktop apps. What is the stack in Clojure that allows me to build such apps? Does it even exist?
There is a good stack in Clojure for building web applications. And it's really inspired by, I believe, Sinatra on the Ruby side, if I remember correctly. Anything you can do in Java, you can definitely do in Clojure. I think the Relevance people they have a lot more experience of this, building apps in a number of different languages for clients. It's not uncommon right now for people to use a Ruby front end to do the very stateful HTML parsing and all that kind of stuff, and have it talk to Clojure code, maybe via a RESTful web service, to do all the heavy lifting. That's one of the patterns that we're kind of seeing emerging in the Clojure world. And there's also the ability to just write the whole stack totally in Clojure if you want. And that's one of the things I was getting at with my Cascade library. I'm seeing a lot more people using Clojure to do, as I said, what I would call the heavy back-end lifting. And I've seen a lot of use of Clojure inside Hadoop, which is sort of the open source version of Google's big MapReduce, the way of taking a complicated data intensive function and splitting it across hundreds or potentially thousands of nodes, and everyone works on their piece of the data. People are using Clojure to do things like analyze flight schedules, to predict airline delays, track large amounts of data from a number of sources in one place. That's been one of the areas where it's getting a lot of traction. On the other hand, people are using it. People have written Swing IDEs for Clojure in Clojure. So as I said, if you want to, you can use it to do anything you could possibly do on the Java platform. And where it really shines is where you can start making use of some of the features, like the lazy evaluation is very, very useful because it allows you to express your algorithm much more clearly and not worry about edge cases and efficiency, because that's taken care of at a lower level by the language. Yeah, it's almost impossible at this point to keep up with the Clojure mailing list with the number of people who are producing libraries and extensions and so forth for Clojure. And it's actually one of the bigger percentages on GitHub in terms of projects. The question is, the code samples seem complex, and you're concerned about maintainability of that code, especially in industrial quantities. Yes, even when I was first learning Clojure, teaching myself Clojure, I don't know if it was 3 or 4 years ago, my first little program that I wrote in it was quite laborious for me, because everything required going to the documentation and trying things out in the REPL. And I was just doing something, I think my goal was to write a short program that could score a cribbage hand. Okay, so I was talking about suits and numbers. I was looking for the right ways to do these things. And it took me a while to put something that simple together, something I could whip out in Java in a few minutes. But of course, in Java, I'd been working in Java since like 98, and Clojure at that point I'd been working on for minutes. So unfamiliarity is an issue. And I hadn't used anything Lisp-like since college, which was a huge gap. Now, when I'm coding stuff up, it comes together faster and more succinctly. And the thing I was trying to express in the slides was that once you are familiar with Clojure, and again, try to remember coming to like Java from perhaps, I don't know if you maybe did BASIC or PHP or some other language prior to Java. A lot of the stuff in Java seemed very unfamiliar. I remember pounding my head against the wall first learning Java in '97 because I had an Objective-C background, and things seemed arbitrarily different and strange and unfamiliar then. Now they seem very familiar, and going back to Objective-C would be hard. So try to see past the unfamiliarity and see the conciseness and expressibility of the language. So how does this scale up? Like any other endeavor, programming endeavor, maintainability is defined by testing and documentation and just all the other aspects of engineering that I think apply easier in Clojure than they would in Java and other programming languages, because of the nature of its approach to functional programming. It's easier to get in and write tests, and you write significantly less code to do a lot of things. It's easier to break things up into smaller pieces and test them independently and combine them. So I think the answer about maintainability is good, but you have to see past your first day shock at seeing a language that has such a radically unfamiliar syntax. Looks like we are just totally done. But I'll be available the rest of today and tomorrow morning to talk in more detail. Just find me in the halls. Thanks very much. It was a lot of fun coming to Paris and giving this talk.